together. Okay. Wait. Okay. Oops. Okay. Now when aerothermoelastic behavior happens, we'll have possibly some. Wait, my mouse is a little bit weird. Hold on a second. Okay. Yeah, so as you might see from the lower right, we'll have some flutter behavior that's catastrophic for the hypersonic vehicles. And then apparently we need to somehow try to, wait, the mouse is so weird. Why is that? Okay, there we go. Yeah, so we need to analyze this whole system as a multidisciplinary system where we involve the hypersonic aerothermal dynamics, the structural dynamics, and the heat conduction. And each of them each have their own challenges, but of course the main challenge would be the coupling between each of these disciplines. Okay. I think I will need to switch back to my regular mouse. But can you, Sishan, can you see the mouse directly?
Yeah, I can see.
Okay, yeah. The laser point is a little annoying. Okay, so then over the years to tackle this problem, we have developed this kind of a framework. Now we call it HYPATE-X. During my PhD, it's called HYPATE. And then over the past 2 years with my colleagues at Penn State and Arizona, we kind of extended to include more capabilities. And as you can see down here, actually today we'll be focusing on the reduced order model side. Although many of the modules are still under development, but we'll mainly highlight some interesting applications on this lower left hand, where we model the aerothermal loads in hypersonic flow. Now, first of all, let's think about what's the fundamental challenging component in this modeling procedure. And here we are taking this aerothermal sub-problem of the fluid thermal structural interaction phenomenon. So in this flow field, we are essentially having this high-dimensional dynamical system, nonlinear dynamical system that's used to characterize this whole thing. And to start with, we have a very high number of states, maybe millions or even billions for complex geometric configurations. This is when if we want really high resolution of the flow field using like LES or DNS. And then the other thing is that now we are dealing with an interactional problem, meaning that we have the flow field interacting with the other physical domains. And as a result, we are going to have some input from the other physical domains to this fluid domain. And the fluid domain is going to react on those other physical domains. This gives us like a high dimensional input and output. And furthermore, if we kind of want to control this system, then we also need to add some control commands. And as you see, these are some continuous structures, unlike the regular ailerons and so on, which only have one DOF. And here we really have this challenge of high-dimensional optimal control, lower design, and maybe high-dimensional EQ problems, which are nasty to tackle. And so far, we have only thought about like treating it as just one specific case of dynamical system. However, further, if we want to further design or optimize this whole system, then we even have one more set of high-dimensional variables, namely the design parameters. And this basically poses a gigantic design space for this whole problem, which yet is another challenging component of this problem. Now, to give you a little more concrete example on what we might see, or what we should expect for this, now I call it a complex interactional problem. Let's think about, on the lower left case, we see this a panel with many strangers. It's a rather complex structure for the surface of a hypersonic vehicle. And as you can imagine, we have this kind of structure, and when it deforms, we probably should see a very non-uniform, maybe grid-like deformation patterns on the surface. And this poses this, again, a high-dimensional structural or thermoelastic input to the system. And another example is on the lower right. The idea is that we are having some shock impingement on the surface, and this causes flow separation, which is really adverse for the aerothermal environment for the structure. So some researcher has been figuring out how we actually deform the surface a little bit so that we can eliminate the flow separation. And again, here you can see that we are having like highly nonlinear surface deformations. These are just another example of what we are needing here. We are, for the realistic FTSI, the flow thermal interaction problem, we need to deal with very nonlinear and a very nonlinear deformation and low temperature. And that corresponds to the input component that we discussed in the earlier equation. And furthermore, if we want to design this whole thing, then of course we will need this configurational parameters, which again could be a high-dimensional parameter. And that's for practical design, but in our current methods, where we are standing at, it's or dealing with simplistic things. For structures, we think about sinusoidal deformations. For temperatures, we think about maybe polynomial temperatures, which, as you can see, they are totally like far from the truth, and it's difficult to handle these high-dimensional inputs and parameters. Then it comes to the question like, what are the options if we really want to tackle this directly, this full order model on the top right, where if you recall the x, u, and the mu, and the z here, they are all high-dimensional. So here I have made a graph. So it's probably something you have seen sometimes. On one end is like we have the model that's mostly based on physics. On the other end, it's mostly based on data. Now here I'm adding one more axis, like if we think about in terms of more like a static problem, if you do aero structural optimizations, then most of those are maybe static. Like the structure only deforms due to the aerodynamic force, but it doesn't vibrate according to that. And but on the other hand, we have the more dynamic ones, like now the structure actually vibrates, so that the motion is governed by a differential equation. And this, for example, is a limit cycle oscillation kind of analysis. And now to tackle this full-order model, apparently the most brutal force way is basically we do some kind of maybe surrogate modeling if we are dealing with a static problem, where we sample a range of inputs and outputs, inputs and the parameters, and then we get that output. However, you probably are not know very well with the curse of dimensionality, right? The u and the mu here, they are maybe all on the level of thousands. which really we cannot sample efficiently for the parameter space. And on the dynamic side, we might be essentially thinking in terms of identifying a dynamical system that emulates the dynamics of the full-order system. And here since we are thinking in terms of a interactional problem, we don't need to worry about what's like in this state. We can just think about what transfers from my high-dimensional to my high-dimensional output. This has been quite useful. For example, in aeroelasticity, we can do these generalized aerodynamic functions that transfers the input to the output in an efficient manner. However, this kind of approach kind of have this issue, like these system dynamics are only for one design parameter, one set of design parameter. So when it comes to like if we want a set of system parameters for different sets of design parameters, then here comes the problem. How do we do that? There are still some work on that, but it's still ongoing, and we are not sure how far we can go there. Now these are the purely data-driven side. We can also think on the other hand, where we do this purely physics-based. Here you can, when we look at this model, you can just think it in terms of the runs with a turbulent closure. And as you know, that's more like a approximation from the more high fidelity tools like DNS. And here we can kind of learn or calibrate the turbulent closure model here, and then we can reduce the total number of degree of freedom to slightly lower, maybe from billions to millions. And this kind of model, they generalize well to like different design parameters or the different input variables. But as you know, it is still runs, so it still takes time to run. And that's the main drawback on this other end of the spectrum. Now, if we move a little further towards the middle of the spectrum, one thing that we encounter is then this so-called projection-based ROM, where we express the flow field in terms of several or maybe tens or hundreds of modes, and then we just capture the evolution of this model coordinates. But then here again, we come to the question, like for this, if we consider these control inputs, or we consider the design parameters, how does these modes change? And now we need to think about the evolution of these modes in some high dimensional space. And again, this is something I think, at least to my knowledge, it is still under study and not well resolved. So then coming to the middle, then that's actually one thing we are recently thinking about. Can we maybe follow some idea in this data-driven turbulent closure ideas, but derive something that's entirely new, some new governing equations that we can actually reduce the number of states from millions or billions to maybe just a few, or maybe just tens of variables. And this leads to the physics-infused ROM that we'll later discuss. So yeah, here's just a summary of the several types of ROMs that we thought about. Here we mainly want to think about several things. Two things. One is that whether they are generalizable to different system parameters. And the second, how computationally costly is it? And in our group, we mainly focus on the lower four items. Namely, we for sure want faster computations, and gradually we want increasingly high generalizability to system parameters. And we are exploring all these for specific problems, because for some problems, like they are having their own ranges of suitability to the specific problems that we are looking at. Now, in this talk, I will mainly focus on these two. One is surrogate modeling, but I want to talk about the correction part. And then there's also this physics-infused ROM that recently I get quite interested in. Okay, so now, first of all, let's start with the first thing, the surrogate. And this study is mainly driven by our need to study this high temperature effects on the FTSI response. Now, first of all, let me explain a little bit on what is high temperature effects, or like why do we care about these high temperature effects? So as the name implies, this is about when the gas is at high temperature, then the molecules in the gas might start to dissociate, or even having chemical reactions between each other. And this might happen at sometimes higher Cruz Mach number, and in specific aircraft components. Like, for example, this inlet ducts, it can reach maybe over 2000 K at Mach 8, and that's likely to introduce high temperature effects. And if we have these effects, then it's actually rather challenging to predict the heat flux accurately. And here's a study from my colleague from Arizona, and then they are trying different kind of models and try to capture these experimental measurements. And it turns out they have to use the most complete set of physics, including the high temperature effects, to capture all these sudden drops and sudden peaks in the flow field. And this prediction or the effect of high temperature effects can really lead to maybe very erroneous aerothermoelastic analysis for the structure. And that's one of our prior study that we found that using the low fidelity model and the higher fidelity model, the conclusions will be totally different. One says having high temperature gives a better tolerance. The other says no, higher temperature actually gives you a shorter stability boundary. And this is really a disaster. And this motivates us to try to assess the high temperature effects more appropriately. But then this comes to this question, or this issue, that conventionally we are mainly doing this Gaussian process regression to build the surrogate for the FTSI analysis, where each of these samples, they are, for example, a Rans solution. And typically we require maybe 1,000 solutions to build a converged ROM. However, for our high temperature problem, it turns out one solution can take a week to generate. And that's already on like maybe a dozen core CPUs or like a computer cluster. And that's really then impossible that we do this 1,000 solution just to build the surrogate. And then what we thought about is then to use this multi-fidelity approach, where we introduce this lower fidelity model, which we can generate these high number of solutions very easily. And then we introduce maybe 100 or 10 solutions for as a more like a correction. And then we can fuse them using a multi-fidelity GPR. And then we again can find a aerothermal surrogate that can be used for the FTSI analysis. So here, just to give you a little bit background on the surrogate model, here I'll show a hierarchy of surrogates. So first of all, it's our conventional ROM, where the green column is our output is a high-dimensional vector output, and the purple columns, they are essentially a collection of the principal components of our samples, the sample output. And then we multiply this these modes with our Gaussian process models. They are just a few scalar GPRs that are independent from each other. And here you can think these GPR as the model coordinates of these principal components, or typically in the field we call those POD, but it's essentially the same thing. But now if we think further, in this this upper graph, it's actually in some sense the same as the lower one here, where we have a matrix of coefficients of correlation. And now that these GPRs, they are not correlated to each other, that means our correlation matrix is actually a diagonal matrix. But certainly we can make it fully populated, and that gives us a multivariate GPR, namely this entire thing, this small matrix multiplied by the GPR here. And this whole model then has to be trained using by a little more complex GP model, where instead of a correlation function, we have a matrix correlation function, which goes like this. Now here then you probably can see that we have a matrix which are the principal components, and then we have the coefficients of correlation. They are just two sets of matrices, and it somehow maybe doesn't make sense that we just keep this matrix multiplication inside this model. I mean, they are just the numbers eventually. So then the thing is, why don't we just combine them, and then we learn the coefficients of correlation directly, but hopefully they can also represent the principal components of the output. So this leads us to what we call this a full multivariate GPR, where we just get rid of the principal components. Now to do this model, it's the same thing. We still use the same multivariate GPR to characterize this process. But here, to reduce the dimension a little bit, we introduce this a classical model called a linear model of co-regionalization, where we construct this matrix correlation function using something similar to a spectral decomposition of a matrix, where we have a few scalar correlation functions on the diagonal, while the B here is actually a thin and tall matrix. So with this, we have a kind of a low rank matrix correlation function. Now, if we go further, then we can introduce the effect of multiple fidelity data. And here we put an example for just two sets of fidelities. We start with a low fidelity component, which is still a multivariate GPR. And then we multiply with a correction factor. And then we add another GPR that characterize the difference between the low fidelity and the high fidelity components. And in this manner, we obtain this what we call the M2 GPR, where it's essentially a mixture of the low fidelity and the high fidelity data. Now here we will just do a very quick demonstration of this model. So here we consider a 2D problem. And here we define the deformation using two sinusoidal modes. And for low fidelity data, we consider all these blue dots, which are, we have 100 samples. While for the high fidelity data, we actually also generate 100 samples over each of these blue dots. But when we do the training, we only consider these red crosses. So we only have 10 high fidelity data for training, while the other 90 high fidelity samples, they are for testing. And then here's what we get. For the high fidelity test samples, the maximum error is only about less than 5%. And on the lower end, many of them are like even only 1% error. And here's a little more details on what on some specific samples. And here you can see the low fidelity data. It kind of approximates our high fidelity data that's in solid line, but it's still quite off. However, with the correction from the M2 GPR, we are able to generate some prediction that's rather close to the high fidelity data. Now here's one takeaway actually I want to share. So like even if you don't do this high-speed flow or you just want to try these multi-fidelity models, so what we learned in this process is that most models converge, but it's just some models converge faster. What do I mean here? So here we did two tests. On this upper panel, we consider only 4 POD modes, or like a rank 4 correlation matrix for the M2 GPR. So it turns out the conventional surrogate, it doesn't converge at all. It keeps having this 10% error. And only the M2 GPR converges. So that might give you a feeling that with this more complex model, we are able to achieve higher accuracy. Yes and no. The M2 GPR achieves higher accuracy only when there's not enough samples when compared to other surrogates. But if there are sufficient number of samples, all of these models will converge given a sufficient number of parameters. And that's what happens in the second plot, where we consider 6 POD modes. And then that gives a sufficient amount of information for the model to fit the data. What we see that even for the conventional model, it converges as the number of samples increase. So the real advantage of these multi-fidelity or multivariate GPR is more about when you don't have many training samples, then possibly you can achieve a good accuracy even without generating more samples. And here's one detailed analysis of these modes, but we'll skip for now for the sake of time. And then we continue to apply this surrogate to some canonical high temperature configuration, where we have 2 compression surfaces. And as you can see, due to the super high Mach number, we get very complex flow structures. And that's definitely more complex than what we learn in like compressible flow with the shock interactions. And then to make it simpler for our structural analysis, we adapt this model for a double wedge configuration instead of a double chrome configuration. And here we basically create a few data sets. We here actually consider two sets of low fidelity data sets. One is very simple engineering models or analytical models. We call them AM. And the other set is slightly higher fidelity, which is a perfect gas runs. For each of these, they are relatively easy to generate. So we generate 500 samples, as you see on the left. While for the high fidelity data, we generate these, we use our Arizona collaborators solver. Well, they generate the data for us. So we only see the data. And that's about 31 samples, as you see on the right. And then before we go to the results here, I'll show a little bit on what would happen if we include the surface deformation in the high-speed flow field. So basically, it adds even more complexity to the already complex flow field, where here you can see the choking of the flow and some separation over the turning point. And these are for sure, it's really hard to resolve accurately. Now coming back to our surrogate modeling, here then it's actually what we found really interesting, that the higher fidelity doesn't necessarily give you better results. And here I'm showing three sets of models. One is that using the high fidelity, namely here HT means high temperature, and plus the lower fidelity analytical model. The analytical model, that's the lowest fidelity data. And then we also have a model, the HT plus the RANS dataset, a little bit higher fidelity. And finally, we only consider the high fidelity dataset. And here's what you get. So using HT and AM, it's achieving the best accuracy, slightly or somewhat better than the high temperature only dataset, which is a single fidelity dataset. However, if you look at the high temperature plus RANS dataset, it actually worsens the prediction, sometimes worsens a lot by 20%. Oh, sorry, by maybe 12%. And if we take a closer look, for example, on the like this third case, and here's what's happening or what's wrong with the combination of high temperature and the RANS dataset. So on the top is just the prediction of the heat flux, which here you can see in the RANS prediction, we get so many small oscillations that essentially contributed to those errors. And plus here, we get some non-physical peak in this drop. And then if we check the lower fidelity component of the surrogate, we actually found that this red line from the RANS model is actually totally off from the true prediction. The dashed line here, that's our high temperature sample. And as you can see, you get two peaks around in the middle. However, the RANS actually is having a totally different trend. It's having peaks at the leading edge and at a later stage. While our analytical model is kind of maybe overly smooth, but it's kind of capturing the dropping trend of the true high fidelity data set. And this difference in the low fidelity component gives major gives a challenge for the correction component of the multi-fidelity data set. Multi-fidelity surrogate. And here, as you can see, the runs component it has to correct for this bigger difference, which causes these small oscillations, and that eventually leads to the these erroneous oscillations in the prediction. So here we figure out actually a way to examine like which data sets are like easier to be combined together to get a better fidelity model or higher accuracy model, and this is achieved using these subspace distances, or specifically the geodesics in Grassmannians. So here, if we measure the difference between the different data sets, actually the runs data set is a little more distant from the high temperature data set when compared to the analytical model. And that correlates well to the trend that we are seeing. The model combined with analytical model is better than the model combined with the runs model, even though the runs model is supposed to be having higher fidelity. Now, again, for the sake of time, I'll skip this thing that's mainly maybe of interest to the hypersonic guys. And then let's think about the other thing, what we call the physics infused ROM. Here we really want to do some surrogate or reduced order model that's generalizable to different inputs. So now if we turn back to the our full order model, we still have this equation. Now, in the literature, or like during the development of any engineering subjects, we always have this low order model. These are from like first principle methods, and it contains much less states. Here, basically we might have a differential algebraic equation in place of this nonlinear high-dimensional dynamic system, and but in this process we do need to introduce some auxiliary variables to complement the missing variables or missing states. And here to give you some concrete example, for example, when we deal with a boundary layer, the full order model would be our Navier-Stokes equation, and has states like the density, velocity, and energy, and so on. But if we just want to look at the boundary layer, then we can take a look at the momentum integral equation, where now we actually only have some very simple states, which are the boundary layer thickness. But to fully characterize or close this integral equation, we do need to introduce some auxiliary variables that are like shape factor and the skin friction. And a similar story for a slender structure, where from undergrad structural class, you probably know that since it's slender, we just make it Euler-Bernoulli beam, which is just a 1D problem, as opposed to the three-dimensional elasticity equations, which requires you to resolve a three-dimensional displacement field. But of course, using this lower order model, they don't really fully capture what you see in the full order model. So here comes our idea, like we kind of correct these auxiliary variables. We replace this algebraic equation with possibly a augmented differential form, so that the new auxiliary variables, when it goes back to the differential algebraic equation, it gives us the correct output that we are interested in. So in other words, we can transfer this in this way, where we parameterize the augmented equation that we want to learn from data. So we have the parameter A and theta here. And then we pose this as an optimization problem, where we want to make sure that our output is like matches our full order output. And then we just try to do the argument on the parameters A and theta. Now we then tested this methodology on on our hypersonic aerothermal load prediction problem. Well, here you see a very simple flow field where we have a small bump in the middle, and at a high-speed flow, we are kind of having this combination of shocks and expansion waves. And for this, we actually can, if we think in terms of the boundary layer, then essentially we are having the deformation in the middle, which is like our input. And then we have a boundary layer that's growing over the surface, leading us to the effective shape. And then outside the effective shape, we can consider the flow to be mostly inviscid. And as a result, we, like from maybe about 50 years ago, people have already have this model, turbulence viscous inviscid interaction model, which is essentially an augmented form for the momentum integral equation for boundary layers. And as you can see, this is a differential algebraic equation, and it kind of captures some of the physics in the flow field, but still misses some details. And hopefully using our methodology, we can complement those missing physics and increase the accuracy or the fidelity of this model. And to start with, we first rewrite this in the form that you have seen earlier, in this more formal DAEs, where here are just giving an idea on like the analytical form of these models. But the thing we are getting at would be, then we introduce some corrections into the auxiliary variable equations. And hopefully with this correction, we can actually improve the accuracy of the output. And here we consider a algebraic multiplicative correction instead of making this equation differential. And here is because we choose this approach for demonstration of the concept. And yeah, here to find this this correction term, then we perform a optimization where we yeah, just run this a few times to find the correct values. And here is our current methodology, but it's still evolving, where we have these 3 stages, not counting the stage 0. So here I'll go through this quickly to show you the procedure. So we first start with the Rance solutions, which is quite normal. And then we continue to the DAE-Constrained optimization, where here we actually consider a combination of several ThermoElastic inputs to the boundary layer. And then we do some sampling on the deformation and water temperature. And then for each of those Rance solutions, we do an optimization like this. And for example, if we have a panel deformation like this as the input to our system, and then we would get some pressure on the surface like this. The blue line is what we get from the first principle-based low-order model, which is kind of quite off from our black line, that is our hyphatate model. But from the optimization, we are able to find almost exactly the pressure that we want that matches with the runs solution. And in this process, we generate a set of correction factors that actually only works for this case. But then we collect these correction factors that we find and combine them into a training data set. And then the next is that we combine these training data set and code it into a learning model. In this case, we just use GPR for simplicity. And this GPR will map the different equation states to different correction factors in the scenario that's not in the training data set. And then as a result, we will get this augmented TVI model or this augmented reduced order model. And here I'm just giving a quick example of what we are able to achieve. Here we are considering some displacement and wall temperature that's entirely doesn't exist in the training data set. And also a Mach number that doesn't exist in the training data set. And here we are able to capture almost exactly our the pressure and the heat flux of interest, which is our output of the fluid system. And as a comparison, the uncorrected, the lower order model is rather off, especially for the heat flux. It's about a 20% error. And then now with this this new what we call the ATVI model, then we are able to couple that to the structural and the thermal solver to essentially to reproduce this kind of aerothermoelastic response. Here I'm just showing two quick examples where we considered like these two cases with varying boundary conditions, which actually is not quite doable by the conventional surrogates. However, we are able to do those cases using our new reduced order model. And as you can see, using the low order model, it's producing about 10% errors over the simulation, which is rather not acceptable. But on the lower end, we are able to achieve rather accurate result, about maybe 1% error for the FTSI simulation. And here the lines are a little messy, but here we are mainly showing the pressure and the heat flux distribution over the different time steps. And you can see here that the blue lines, they are kind of much less accurate when compared to the run solution in black and the new model in the red. And with this, we are essentially able to explore in a more extensive parametric manner about these different aerothermoelastic configurations for hypersonic vehicles. So now concluding remarks. Here today we are mainly talking about how we tackle the systems of high dimensional input, output, or design parameters. And to do this, we try to propose some different surrogate or reduced order modeling methods. One is this M2 GPR, where essentially there are two key takeaways. One is that it is a good model. It's a model that can generate accurate prediction with less samples, but it doesn't really always give you a more accurate model, because when you have sufficient samples, the single-variate GPR will also perform pretty good. Just you have this extra cost of generating samples. And the other thing which might be more interesting is that combining the data sets of higher fidelity doesn't really give you better results. In other words, the physical fidelity doesn't play or play too much in the M2 GPR training or the multi-fidelity GPR training. What really matters is how similar are the data sets, the low fidelity data set to the high fidelity data sets. And here we say that we use this geometric distance to measure this similarity, which turns out to be or empirically works well for the GPR. And then we introduced this physics-infused reduced order model, where we demonstrate this methodology on the high-speed boundary layer model. This whole thing is done by my clever master student, Carlos, which is now working on his master thesis. And this approach, we have shown that it's generalized robustly to like arbitrary inputs or parameters, or in some sense, due to the functional form of the model, this is applicable to infinite number of inputs and parameters. And that's all I have today. And thank you for listening to my presentation.
Yeah, thanks, Daniel, for this very informative and it seems and the M2 like Gaussian regression seems also a fundamental idea. So it's definitely very interesting. So is there any question from the audience? You can raise your hand or just put things in the chat. So I actually had a lot of questions. One of that is how did you get beta? Could you clarify that?
Get what?
I see, for the part 2, you have this like coefficient scalar field. I think it's like you do an optimization problem and you found beta. Is that the idea?
Yeah, that's right. So so we for each run solution we do this optimization and then find the beta, right? And then these beta correspond to the specific states and inputs for this specific case. So we kind of write this up in a table like this. But our and our next step is actually try to directly parameterize this this correction using some like a network, a neural network, and then we directly train that network parameter over this, which is more direct.
Yeah, that makes sense. So it's like all you can do maybe found beta and then use that as a data, like a data point. I mean, you can train another mapping from the state variable to beta to get this model. So like two-stage approach.
Yeah. Currently it's two-stage, which is indirect. We can take a direct approach.
Yeah, that makes sense. Yeah. Any question from the audience? So, Danny, could you, because right now I'm like working on transition, could you elaborate that? Do you think like, have you considered transition in this like hypersonic aeroelasticity and will that have an impact on this problem?
Yeah, definitely. So physically, if we consider transition, then that will introduce a really peak in the heat flux in the flow field on the wall. That's definitely something we want to like characterize. But the challenge here is that in hypersonic flow, the transition is kind of like more complex. We have these different modes of like different modes of instability, and that's currently more or less like an active field of study. And I think now are you doing like in the transonic or subsonic flow region?
Right. Yes.
Yeah. Actually, then it becomes interesting, like applying your method to like the high speed flow. to see what might happen, like whether,
right.
yeah,
definitely. Okay, any more questions from the audience? So it seems pretty shy. Okay. Okay, if there's no question, let's thanks Professor Daniel again, and we will see you next week on Wednesday. So yeah, thanks Daniel.
Okay.